On July 23, 2015, NASA held a press conference and used a phrase that immediately spread to every major news outlet on the planet. Earth's twin. That was the phrase. Not Earth-like. Not potentially habitable. Twin. And the word did exactly what a word like that is designed to do. It moved fast. Within hours it was in headlines across every major language. A twin, sitting out there in the dark, orbiting a star nearly identical to our Sun, at nearly the same distance our planet orbits ours, taking roughly the same amount of time to complete a year. The story wrote itself. Humanity had been searching for another Earth for decades, and now someone was standing at a podium saying they had found something that looked like the answer. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. I'd love to know where you're watching from and what time it is for you. Feel free to drop your location and time in the comments below. The planet had a name, Kepler-452b. It was discovered by the Kepler Space Telescope, a spacecraft NASA had launched in 2009, specifically to hunt for worlds like this one. Kepler stared at a single patch of sky and watched more than 150,000 stars simultaneously, looking for the tiny, repeating dimming that happens when a planet passes in front of its star. It found thousands of candidates. Most were gas giants, close-in giants, planets nothing like Earth. Kepler-452b was different. Everything about it pointed in the same direction. Rocky surface, likely. Orbital distance almost exactly 1 astronomical unit. Year length of 385 days. Star type nearly identical to our Sun. The Kepler team had been careful with exoplanet language for years, and here they were, using the word twin out loud. The room reacted like rooms react when something genuinely strange has been found. The announcement drew comparisons to other landmark moments in planetary science. John Grunsfeld, then NASA's Associate Administrator for Science, stood up and called it a close cousin. John Jenkins, the scientist who led the Discovery team, used language that was more direct. He described looking at the data for the first time as akin to looking in a mirror. These are not the words scientists reach for when they're describing a minor result. The press conference had the feeling of something that mattered, and the public responded accordingly. The story exploded. Social media ran with the twin framing. Websites posted side-by-side graphics of Earth and Kepler-452b. Comment sections filled up with speculation about what life might look like there, whether anyone was living on it already, whether we had somehow found proof that we were not alone. For a few days, the name Kepler-452b was everywhere. Cable news ran it. Late-night shows mentioned it. The words Earth 2.0 appeared in print so many times that NASA itself started using that phrase in follow-up releases. What made this feel different from previous exoplanet discoveries was the combination. Before Kepler-452b, scientists had found rocky planets, but they were usually too close to their stars or orbiting red dwarfs that bore no resemblance to our Sun. They had found planets in the habitable zone, but those were often gas giants or orbited stars so different from ours that the comparison to Earth felt strained. They had found planets orbiting Sun-like stars, but at the wrong distances. Kepler-452b was the first time the major boxes had all been checked at once. Sun-like star, correct orbital distance, probable rocky surface, year length within a few weeks of Earth's. That combination had never been confirmed before. The excitement was real, and in that specific sense justified. The word twin, though, was doing an enormous amount of work. A twin implies equivalence. It implies that what you know about one tells you something reliable about the other. It suggests symmetry. and the framing and most of the coverage leaned into exactly that suggestion. The planet looks like Earth, orbits like Earth, catches sunlight like Earth. The implication hanging in the air was clear. If it looks this much like Earth, maybe it is like Earth in the ways that matter most. Maybe there is an ocean. Maybe there is air. Maybe there is something living in that air. Nobody on the podium said any of that directly. But nobody had to. The word twin said it for them. What the coverage did not linger on was a number that appeared in every press release, every official NASA document, every technical summary published the same day. 1,400 light-years. That was how far away Kepler-452b was from Earth. 1,400 light-years. It appeared in paragraph 3 or paragraph 4 of most articles, usually right after the exciting part, usually followed by a sentence about how the Kepler telescope had been designed to detect exactly this kind of world. And then the articles moved on. They went back to the twin language, back to the habitable zone, back to the question of whether life might exist there. The distance was mentioned and then quietly set aside, like a number that was interesting but not especially important. That was a mistake, not a dishonest one. Nobody was hiding anything. But 1,400 light-years is not a detail. It is not background information. It is the central fact about this planet, the fact that determines everything else about what finding it actually means, and what we can ever hope to know or do about it. The distance number was in every press release, sitting there in plain sight, and almost nobody stopped to work out what it actually meant. To understand why Kepler-452b stopped people in their tracks, you have to go through the numbers one by one. Start with the orbit. Earth takes 365 days to circle the Sun. Kepler-452b takes 385 days to circle its star. That is a difference of 20 days. 20 days out of a full year. If you lived on Kepler-452b, you would barely notice the calendar was off. Your seasons would arrive at almost exactly the same rhythm. Winter would still give way to spring on roughly the same schedule you have always known. The orbital distance is 1.05 astronomical units, where 1 astronomical unit is the exact distance between Earth and the Sun. So Kepler-452b sits just 5% further from its star than we sit from ours. That is not an approximation. That is not close enough. That is nearly identical. Now look at the star itself. This is where it gets interesting. Most exoplanets found before 2015 orbited red dwarf stars, which are smaller, cooler, and far more violent than our Sun. They throw off massive flares. Their habitable zones sit much closer in. The environments around them are nothing like what Earth experiences. Kepler-452 is different. It is a G-type star, the same classification as our Sun, same color, same approximate surface temperature, same kind of slow, steady, relatively calm output of energy. When astronomers looked at the light coming from Kepler-452, they were looking at something that felt familiar in the deepest possible sense. It was like recognizing a face in a crowd. The star was not merely sun-like, it was a near copy, close enough that the word twin started getting used for the system itself, not just the planet. Then there is the planet's size. Kepler-452b has a diameter roughly 60% larger than Earth's. That sounds like a significant difference, and it is. But it still puts the planet firmly in a category scientists call super-Earth, which means rocky, which means solid ground, which means a surface. This matters enormously. Most of the large exoplanets catalogued before this discovery were gas giants, worlds with no surface to stand on, no ground beneath your feet, just endless layers of crushing atmosphere spiraling down into nothing. Kepler-452b almost certainly has a surface. The density estimates pointed toward rock and metal, not gas. something you could theoretically stand on, something that looked, at least in the numbers, like the ground you are standing on right now. What about seasons? On Earth, seasons exist because our planet is tilted on its axis. As we orbit the Sun, different hemispheres lean toward it and away from it over the course of the year. Evidence suggested Kepler-452b likely has a similar axial tilt, which means it probably experiences the same kind of seasonal cycling that has shaped every ecosystem on this planet. The slow transition from cold to warm, the lengthening days, the shortening nights. None of this is guaranteed from 1,400 light years away. But the probability was real enough that scientists were talking about it openly, and that was a remarkable thing to be talking about. Here is something worth sitting with for a moment. Every one of those similarities had been found before, in other exoplanets, in isolation. There were planets at roughly the right distance from their stars. There were planets orbiting G-type stars. There were super-Earths with rocky compositions. Scientists had seen each piece of the puzzle before. What had never happened, not once in all the years of exoplanet searching before July 2015, was all of those pieces appearing in the same place at the same time. Orbital period close to Earth's. Orbital distance close to Earth's. Star class matching the Sun. Likely rocky composition. Probable seasons. Each one of those characteristics alone was interesting. Together, they were something else entirely. This is why the press conference language was the way it was. NASA scientists are careful people. They are trained to hedge. They are trained to qualify everything with probabilities and uncertainty ranges. But when they announced Kepler-452b, the words that came out were things like older cousin and Earth 2.0. That language did not come from nowhere. It came from staring at a checklist that had never been this complete before, and not having a more restrained way to describe what they were looking at. The star Kepler-452 sits in the constellation Cygnus, roughly where the band of the Milky Way runs thickest in the summer sky. People had been looking in that direction for centuries without knowing anything was there. Then the Kepler telescope stared at that patch of sky for years, watching hundreds of thousands of stars simultaneously, measuring the tiny dips in brightness that happen when a planet crosses in front of its star. One of those dips, repeating every 385 days, belonged to something that looked like home. It is worth taking a breath before the complications arrive, because the complications do arrive. But before they do, the discovery deserves to be understood on its own terms. A planet. Rocky surface, orbiting at 1.05 AU, around a G-type star, in 385 days, with probable seasons. Everything a checklist of Earth-like conditions would ask for. No other planet found up to that point had checked this many boxes at once, and that was before anyone looked at the age. The thing that makes the age of Kepler-452b genuinely unsettling is what 1.5 billion years actually represents. Not as an abstraction, not as a figure in a press release, as actual time measured against things that happened on Earth, things that changed everything about what life is and what it can become. Because when scientists say Kepler-452b is 1.5 billion years older than Earth, they are not describing a minor difference. They are describing an entire second history stacked on top of our own. Start with where Earth is right now. 4.5 billion years of geological activity, chemical evolution, and biological change produced a planet with intelligent life, global civilizations, space telescopes, and the capacity to notice other worlds. That entire arc, from the first self-replicating molecule to a species that can ask questions about its own origins, fits inside 4.5 billion years. Now add 1.5 billion more, Kepler-452b has had that entire journey, and then another 1.5 billion years on top of it, all while sitting in the habitable zone of a stable, sun-like star. To understand what 1.5 billion years can do, look at what happened on Earth during that same length of time. Go back 1.5 billion years from today, and you arrive in a world that is almost unrecognizable. There are no animals, there are no plants on land, there are no forests, no insects, no fish, no bones, no shells. Life exists entirely in the ocean, almost entirely as single-celled organisms. The most complex things alive are early eukaryotes, cells with a nucleus, a development that was itself one of the most significant transitions in the history of life on this planet. Everything that came after, every organism with more than one cell, every creature that has ever crawled or swum or flown or walked, evolved in the 1.5 billion years between that world and this one. That is what 1.5 billion years produced on Earth. That is the unit of time we are talking about. If life emerged on Kepler-452b early in its history, somewhere in its first billion years the way microbial life appeared on Earth, then it has already lived through an equivalent of our entire evolutionary story. The Cambrian explosion, which produced the basic body plans of nearly every animal alive today, happened about 540 million years ago. That was less than 600 million years into the multicellular era. On Kepler-452b, that threshold could have been crossed twice over. Whatever was swimming in its oceans when Earth's first animals were just appearing could have had another billion years to keep going. The arithmetic here is not reassuring. This comparison reveals something important about deep time. A billion years is not merely a larger number than a million years. It represents a qualitatively different scale of planetary possibility and change. In that span, climate can shift dramatically, continents reorganize, and stars age measurably. Kepler-452b has experienced these transformations multiple times over. The older a world becomes, the more cycles it endures, and the greater the accumulated possibilities for life to branch into new forms and explore ecological niches. Here is the thing worth sitting with. Evolution is not a straight line toward anything in particular. It doesn't aim at intelligence or complexity or civilization. Most lineages on Earth went extinct. Most of the time that life has existed on this planet, it did nothing that would look dramatic from the outside. Microbes dominated for 3 billion years before anything interesting arrived. So there is no guarantee that 1.5 billion extra years on Kepler-452b produced anything more complicated than better bacteria. That is a real possibility. The extra time doesn't automatically mean anything emerged from it, but the possibility that it did is the part that pulls at you. On Earth, intelligence appeared roughly 300,000 years ago in its modern form. Civilization, the organized kind with cities and writing and technology, is about 5,000 years old. Radio transmission is about 130 years old. That entire chain of developments, from the first Homo sapiens to the first radio signal, took less than 300,000 years. On the scale of planetary history, that is a rounding error. If Kepler-452b had a similar chain of developments, starting from a comparable baseline but 1.5 billion years earlier, the numbers become genuinely strange to contemplate. A civilization 1.5 billion years more advanced than ours is not a concept that scales to anything familiar. We have been using electricity for about 200 years. We sent our first object out of the solar system less than 50 years ago. Projecting that curve forward by 1.5 billion years produces something that does not resemble anything we can describe. Scientists are careful about this line of reasoning. It stacks assumptions on top of assumptions, and each assumption could be wrong. Life may have never started on Kepler-452b. Complex life may have started and collapsed. Intelligence may have appeared and disappeared without leaving any mark we could detect. The history of life on Earth is full of extinction events that nearly ended everything, and a planet 1.5 billion years older has had 1.5 billion more years of asteroid impacts, volcanic episodes, and stellar variations to work through. Survival over geological time is not guaranteed. It is, if anything, improbable, and yet the question does not go away. It sits at the back of every careful sentence scientists write about this planet. Kepler-452b is old enough that if the conditions were right, and if life got started, and if something like the Cambrian explosion happened there, and if intelligence followed on any kind of comparable timeline to our own, then whatever emerged there started its journey before the Earth even formed. Our planet did not exist yet. The solar system was still assembling, and somewhere 1,400 light-years away, something could already have been looking up. Whatever that head start produced, if it produced anything at all, we have no way to know, because of a problem that starts with a number. 1,400 light-years is a number that looks manageable until you try to convert it into anything a human being can picture. Start with something simple. Light moves at roughly 300,000 kilometers per second. In 1 second, it crosses a distance that would take a commercial airplane about 33 years to fly. In 8 minutes, it travels from the Sun to Earth. In about 4 years, it crosses the gap to our nearest neighboring star. So when you hear 1,400 light-years, you might think that sounds like a lot of 4-year trips stacked together. And it is. It is 350 of them. That number, though, still does not land. The human brain was not built to feel the difference between vast and incomprehensibly vast. Both just feel like far away. Here is a way to feel it. The fastest spacecraft humanity has ever launched is New Horizons. It left Earth in 2006, swung past Jupiter for a gravity boost, and reached Pluto in 2015. 9 years to cross the outer edge of our solar system. At that speed, roughly 59,000 kilometers per hour, the travel time to Kepler-452b works out to approximately 26 million years. Not 26,000. Not 260,000. 26 million years. That figure seems almost designed to be meaningless, so it is worth holding it next to something real. Modern humans have existed for around 300,000 years. The entire span of our species, every generation that ever lived, every language ever spoken, every war ever fought, every city ever built and lost, fits inside 300,000 years. The journey to Kepler-452b at New Horizons speed would take 87 times that long. Human civilization, the part with writing and agriculture in cities, is roughly 5,000 years old. The journey would take 5,200 civilizations worth of time, stacked end to end. By the time a spacecraft launched today arrived, the evolutionary pressures alone would have had time to produce something unrecognizable from the people who sent it. The Kepler mission itself lasted 9 years, from its launch in 2009 until its failure in 2013. In that span, it catalogued more than 2,600 confirmed exoplanets across the galactic neighborhood. Kepler-452b was among the final discoveries, found buried in archival data processed long after the spacecraft systems failed. The planet had existed for billions of years, wholly indifferent to our awareness of it. We had been searching for only the briefest moment in cosmic time, the precise historical moment when our technology became sophisticated enough to detect it, remains almost absurdly arbitrary. Could we observe the destruction of a star as the moment unfolded? That question gripped people for months. Here, the question is quieter but stranger. We have found what looks like a twin of our planet, and we cannot go there. Not eventually, not with better funding, not with a political will we currently lack. The barrier is physics itself. The speed of light is the universe's absolute ceiling, and even at that ceiling, the trip takes 1,400 years. A civilization that launched a light-speed vessel today would need to still exist, still be listening, and still care about the mission 14 centuries later to receive anything back. That is longer than the gap between us and the fall of the Roman Empire. And we have no light-speed vessel. We have no concept for building one. The fastest thing we know how to make moves at a fraction of a percent of the speed of light. Every proposal for closing this gap, whether laser sails, antimatter drives, nuclear pulse propulsion, requires either physics we have not discovered or energy we have no way to generate. None of them change the fundamental picture. They make 26 million years shorter. They do not make it manageable, even at 1% of the speed of light, which represents technology far beyond anything currently on a drawing board. The journey takes 140,000 years. That is still longer than modern humans have existed. There is something almost mocking about the way the number sits there. 1400. It does not even sound that large. You have probably driven farther than 1,400 miles on a road trip. The mismatch between what the number sounds like and what it actually represents is part of what makes the distance to Kepler-452b so difficult to sit with. The press releases used it casually. 1,400 light years, right there in paragraph 2, tucked between facts about orbital periods and stellar types, as if it were simply another measurement, as if it were the sort of thing a person could absorb and move past. Nobody in the 2015 headlines wanted to work through what it meant. The story was about discovery. It was about finding a twin. The distance was listed because it had to be listed, and then everyone moved on to talk about orbital periods and habitable zones, because those were the exciting parts, the parts that sounded like hope. The distance was the part that closed the door, and closed doors do not generate the same headlines as open ones. To understand why this is so unsettling, you have to hold two facts in your mind at the same time. First, we know this planet exists. We have measured its size. We have calculated its orbit with precision. We know the type of star it circles, how long its year lasts, how long it has been sitting in its current position. We can describe Kepler-452b in more physical detail than anyone could describe a distant continent 5 centuries ago. The knowledge is real and specific. Second, we cannot go there, not in any timeline that connects to human civilization as it currently exists, not in any timeline that connects to human civilization as it might plausibly exist. The knowing and the unreachability sit side by side, and that combination produces something that does not have a clean name, visible and permanently out of reach. That is the terror the distance number was always carrying. It is not the terror of the unknown. It is not the terror of something hiding in the dark. It is the terror of a window you can see through but never open. We can point telescopes at the system. We can study the light that left it 1,400 years ago. We can run the models and write the papers and have the arguments about whether life could be there. All of that is available to us. The planet itself is not. We have named it, described it, argued about it, and we are no closer to it than we were the day we found it. Set aside the distance for a moment and imagine you are actually there, standing on the surface of Kepler-452b, not traveling to it, not approaching it from orbit. Just there, suddenly, boots on the ground. The first thing you would notice has nothing to do with the sky or the air or the temperature. It would be your own body and how wrong it feels. Kepler-452b is roughly 5 times the mass of Earth. That mass translates directly into surface gravity, approximately twice what you experience every day. This is not an abstraction. Pick up any object near you right now and imagine it suddenly weighing double. Now imagine that object is you. Every step requires more effort. Your cardiovascular system is working harder just to keep blood moving upward against a pull that is stronger than anything your body was built to handle. Climbing a single flight of stairs would feel like climbing two. Standing still would feel like standing in deep water. Researchers who study high-gravity environments describe the experience as a constant, unrelenting pressure that the body can partly adapt to over months and years, but never fully dismisses. Your bones would actually begin to thicken. Your muscles would densify. Your heart would grow stronger to compensate. Scientists who study long-duration spaceflight in reverse, people returning to Earth from extended low-gravity missions, give a useful picture of what the opposite process looks like. Coming back to Earth's gravity after months in orbit is described as crushing, exhausting, disorienting. Kepler-452b would be that experience, but permanent and roughly twice as severe. The sky above you would not look like anything from Earth's surface. The planet almost certainly has a thicker atmosphere than ours, driven partly by the stronger gravity holding gas closer to the surface, and partly by billions of years of geological outgassing. More atmosphere means more cloud cover. Not overcast in the way that a grey November feels overcast in northern Europe, but something denser. The kind of sky that diffuses sunlight before it reaches you, where the star above is a bright smear rather than a sharp disk. Something like standing inside a greenhouse, or in the highlands of a tropical mountain where cloud sits at eye level and never quite lifts. The light would feel muted, warm probably, but indirect. Beneath your feet, the ground itself is unlikely to be quiet. A planet that has been geologically active for 6 billion years and retains the internal heat generated by 5 times Earth's mass of radioactive elements does not calm down easily. Earth, at 4.5 billion years old, still produces eruptions that reshape landscapes and push new crust up through ocean floors. Kepler-452b, older and more massive, has every reason to be more active still. The volcanic zones on our planet, places like Iceland, or the region around the Cascades, or the volcanic islands of the Pacific, give some approximation of what standing near that geological restlessness feels like. The ground that shifts, the faint smell of sulfur carried on the wind, the knowledge that what is under you is not static. On Kepler-452b, that baseline may simply be higher. The temperature on the surface is where the picture gets more complicated, and depending on how the atmosphere evolved, potentially far more severe. On Earth, our orbital distance and the greenhouse effect of our atmosphere together produce average surface temperatures around 15 degrees Celsius. Kepler-452b orbits at nearly the same distance from a star very similar to our Sun. If everything else were equal, you might expect similar temperatures, but everything else is not equal. A thicker atmosphere traps more heat. More cloud cover cuts both ways, reflecting incoming radiation, but also trapping outgoing heat. On balance, models suggest that even before factoring in the planet's age and the slow brightening of its star over time, Kepler-452b would run warmer than Earth, not necessarily uninhabitable by that factor alone, but warmer, humid, the kind of dense, pressing heat that certain equatorial regions on Earth approximate, where the air itself feels like a physical substance. Standing there, the full picture assembles, the weight pressing down on every joint, the thick air moving slowly, the sky a pale, diffuse brightness without a clear sun, the distant rumble of geological processes that have had 6 billion years to build toward this moment. These are not the conditions of a world that matches Earth in any comfortable, easy sense. They are the conditions of a world that shares certain structural parameters with ours, while differing in ways that would matter enormously to any biology that tried to exist in them. The body comparison is worth staying with for a moment. Scientists who study what double gravity would do to human physiology over generations describe something genuinely strange. The adaptation would be real. Bones would become denser. The heart and lungs would restructure over time. The frame of anyone born into that gravity, across many generations, would likely be shorter, broader, lower to the ground, more surface area relative to height. The biology of a world with twice the gravitational pull quietly reshaping whatever lives there into something better suited to survive it. If anything did evolve on that surface, it likely looks nothing like what Earth produces. The pressure of 1.5 billion additional years under twice the gravity points somewhere different, and none of this accounts for how the planet got to where it is today. The surface conditions described here, the heat, the clouds, the volcanic activity, the dense air, assume a planet that made it through 6 billion years orbiting a slowly brightening star while retaining a breathable, or at least structured atmosphere. That is the optimistic reading. The atmosphere could have evolved in a direction that made surface conditions far more extreme than anything described here, driven by feedback loops that compounded over billions of years in ways that have no clear analogue in anything Earth has experienced. And that is assuming the atmosphere cooperated at all, which after 6 billion years orbiting a slowly brightening star is not a safe assumption. Stars do not stay the same brightness their entire lives, and this is a fact that changes everything about Kepler-452b. It sounds like a small detail, a gradual shift, something happening over timescales so vast that it barely registers as a concern. But when you work out what it means for a planet that has been sitting in the same orbit for 6 billion years, the detail stops being small. It becomes the central problem. Because the star that Kepler-452b orbits today is not the star that Kepler-452b formed around. It is older, it is hotter, and it has been getting steadily brighter for longer than Earth has existed. To understand why this matters, start with our own sun. When the solar system was young, roughly 4.5 billion years ago, the sun was burning at about 70% of its current output. That is a significant difference. 70%. The early Earth was receiving considerably less energy than it does today, and yet the planet did not freeze solid. The reason for that is complex and still debated, but it involves a thicker early atmosphere rich in greenhouse gases, a different geological cycle, and a planet actively managing its own temperature through chemistry and tectonics. Earth compensated. The planet adjusted. Life, once it appeared, helped regulate things further. The warming happened slowly enough that Earth kept pace. Our sun is now about 30% brighter than it was at the beginning. That 30% increase unfolded over 4.5 billion years, and Earth absorbed it without tipping into catastrophe. Barely perhaps, but it managed. Hold that in mind as you turn toward Kepler-452. Kepler-452 is older than our Sun by roughly 1.5 billion years. It is approximately 6 billion years old to our Sun's 4.5. That means it has been brightening for longer. The curve that describes a star's increasing luminosity over time is not dramatic from year to year, or even from millennium to millennium, but stretched across 6 billion years, the accumulated change becomes enormous. Kepler-452b has been sitting in the path of that increasing radiation for its entire existence, and the question of whether the planet could keep compensating the way Earth has is not one anyone can answer confidently from 1,400 light-years away. Here is the structure of the problem. When Kepler-452b was young, the star it orbited was dimmer. At that earlier, cooler output, the habitable zone around Kepler-452 would have been positioned slightly closer to the star. Kepler-452b's orbit may have sat comfortably inside that zone. Temperatures might have been mild. Water, if it existed, might have been liquid. The conditions that scientists point to when they call this planet a potential twin of Earth could have been genuine at one point in its history. That is not a fantasy. The physics supports it, but stars do not hold still. As Kepler-452 aged and brightened, the habitable zone shifted. It moved outward. The inner boundary, the edge closest to the star where temperatures become too high for liquid water, crept away from the star at a rate too slow to see in any single lifetime, but fast enough to matter across geological time. A planet that once sat inside the habitable zone can, over billions of years, find itself on the wrong side of that inner boundary. It does not move. The zone moves around it. This is not a theoretical concern invented for Kepler-452b. It applies to every planet around every star that ages. Venus almost certainly experienced something similar. Earth will experience it eventually. In roughly 1 billion years, our Sun will be bright enough that the inner edge of our habitable zone will sweep past Earth's orbit, and the conditions that make this planet livable will begin to degrade in ways that no geological or atmospheric compensation can fully offset. 1 billion years is a long time, but it is finite. The Sun is pushing outward, and eventually Earth will be where Venus is now. Kepler-452b is already 1.5 billion years further down that road. If you map out the brightening of Kepler-452 over 6 billion years and compare it to where the habitable zone's inner edge has been at each point in that history, the picture is uncomfortable. Early in the planet's life, it likely sat well inside the zone. As the star brightened, the margin narrowed. At some point, and precisely when is something scientists argue about, the planet may have crossed a threshold. Not a sharp boundary, not a sudden change, a slow compounding shift in how much energy was arriving at the surface and whether the planet's natural systems could continue to manage it. Earth's management system involves the carbon cycle. When temperatures rise, rock weathers faster, drawing carbon dioxide out of the atmosphere and into the ground. When temperatures fall, that weathering slows and volcanic activity replenishes the carbon, warming things back up. It is a thermostat, imperfect but functional, and it has kept Earth in a livable range for billions of years despite the Sun's increasing output. Whether Kepler-452b has an equivalent thermostat operating with equal efficiency is unknown. Its larger size and stronger gravity suggest more geological activity, which could mean more volcanic carbon recycling. But more activity is not the same as better regulation. A more geologically active world might pump more carbon into its atmosphere faster than any weathering cycle can remove it. 6 billion years of increasing stellar energy arriving at a planet that may or may not have adequate compensation mechanisms. The math does not resolve cleanly. What it produces is a range of possibilities, and those possibilities are not evenly distributed between good outcomes and bad ones. The warmer a planet gets, the harder it becomes to cool down again. Water vapor itself is a greenhouse gas. Warm more, evaporate more water. Trap more heat. Warm further. The feedback loop runs in one direction, and once it gains enough momentum, nothing turns it around. Venus is where that loop goes when it runs to completion. The question is not whether Kepler-452b has been warming for billions of years. It almost certainly has. The question is how far that warming has gone. The most useful comparison for understanding what might have happened to Kepler-452b is not Earth at all. It is the planet sitting right next door to us, the one that astronomers once assumed would be Earth's sister and turned out to be something closer to a warning. Venus, slightly smaller than Earth, similar density, similar interior, similar mass. By every rough measurement that would appear on an early exoplanet survey, Venus looks like a twin. And Venus is, by any standard that matters to a living organism, one of the most hostile places in the solar system. The surface temperature on Venus is 465 degrees Celsius. That is hot enough to melt lead. The atmospheric pressure at the surface is roughly 90 times what you feel standing on Earth, equivalent to being nearly a kilometer underwater. The clouds are made of sulfuric acid. Spacecraft sent to the surface in the 1970s and 1980s survived for between 23 minutes and just over 2 hours before being destroyed. This is a planet almost the same size as Earth, formed in the same solar system, from the same raw material, and it ended up there. The question that matters for Kepler-452b is how. Venus sits about 28% closer to the Sun than Earth does. That is not an enormous difference in astronomical terms. Early in the solar system's history, some models suggest Venus may have had liquid water, a milder climate, possibly even shallow oceans. The evidence is contested, but the physics allows for it. What seems to have happened at some point billions of years ago is that the oceans evaporated. Water vapor entered the atmosphere. Water vapor is a greenhouse gas, which means it trapped more heat, which caused more evaporation, which added more water vapor. The cycle fed itself. Temperatures climbed. The oceans did not return. The water molecules eventually broke apart in the upper atmosphere and were stripped away by solar wind. What remained was a thick blanket of carbon dioxide, sitting over a scorched surface with no mechanism left to pull the CO2 back out. No oceans to absorb it, no plate tectonics cycling it into rock, just heat, pressure, and acid clouds permanently. This process has a name. Scientists call it a runaway greenhouse effect. The word runaway is important. It does not mean a greenhouse effect that is getting slightly worse. It means a feedback loop that cannot reverse itself. Once it starts and crosses a certain threshold, there is no recovery. The chemistry that made a planet habitable gets consumed by the process. The water that life depends on becomes the mechanism of destruction. The planet converts itself permanently into something else entirely. Commit this to memory. The difference in orbital distance between Earth and Venus, the gap that separates a living world from a dead one, is about 41 million kilometers. On cosmic scales, that is nothing. It is roughly the distance between Earth and Mars at their closest approach. The margin between habitable and catastrophic is that thin. Gliese-12b sits in that margin. It is a recently studied exoplanet, slightly smaller than Earth, orbiting a cool red dwarf star about 40 light-years away. What makes it striking is where it falls in terms of stellar energy. It receives about 60% more radiation than Earth does, but only around 85% of what Venus receives. It lands directly between them. Scientists who study Gliese-12b describe it as a planetary fork in the road. It could have a temperate surface. It could have undergone a runaway greenhouse and be closer to Venus than to anything alive. The atmosphere, if it has one, would tell the whole story, and right now nobody knows what that atmosphere looks like. Bear this in mind. A planet sitting in that zone between Earth and Venus could have gone either way, and from a distance you cannot always tell which path it took. Kepler-452b is not sitting in the narrow band between Earth and Venus, not at formation. When the planet first settled into its orbit around Kepler-452, the stellar energy it received was probably comparable to what Earth receives from the Sun today. That is the whole reason scientists called it a twin. But stars brighten. Kepler-452 is older than our Sun, and as it has aged, it has grown more luminous. The planet that once sat comfortably in the habitable zone has been edged toward its inner boundary as the zone itself drifted outward. Whether Kepler-452b has crossed that line is unknown, but the physics of what happens if it did is not unknown at all. We have seen exactly that physics play out right next door on Venus, a runaway greenhouse on Kepler-452b would have started slowly, more stellar energy arriving at the surface, slightly warmer temperatures, surface water beginning to evaporate faster than it condenses, water vapor accumulating in the lower atmosphere. Each step small, each feedback loop tightening the next. Over thousands of years, then millions, the climate shifts. The oceans, if there were oceans, begin to shallow. CO2 that once cycled through rock and sea and atmosphere starts accumulating. At some inflection point, perhaps crossed quietly over the span of a geological epoch, the process becomes irreversible. What was once an ocean world becomes a pressure cooker, and the planet that looks, from 1,400 light-years away, like a near copy of Earth, isn't real. It is closer to what a spacecraft would be destroyed visiting within the hour. If that is what happened to Kepler-452b, then the discovery NASA announced in July 2015 is genuinely strange, in a way the press coverage never captured. The planet, the headlines called Earth's twin, the closest cousin humanity had ever found, may be a Venus-class world, not marginally warmer than Earth, not a little more cloudy, a world where lead melts on the ground, where the air crushes, where the chemistry of the atmosphere is hostile to every biological process we know. The phrase nearest twin would carry a meaning nobody intended, not a sibling, a cautionary mirror. What makes this particularly difficult is that we cannot see the surface, we cannot sample the air. The tools that would answer the question simply cannot reach that far with any precision available now or in the near future. We are left with the physics, and the physics says a runaway greenhouse is not just possible at Kepler-452b. It is one of the more plausible outcomes after 6 billion years orbiting a star that has been slowly brightening the whole time. The bracelet of habitability is narrow, and 1.5 billion extra years of stellar brightening is plenty of time to fall off its edge. The habitable zone gets described in press releases as the Goldilocks zone, which is a charming name that papers over a significant amount of complexity. The idea is simple enough on the surface. Every star radiates heat. At a certain range of distances from that star, a planet receives enough warmth to keep water liquid at the surface, but not so much that water boils away entirely. Too close, and you cook. Too far, and you freeze. The band in between is the habitable zone. It sounds like a threshold. Cross it, and you have a world where life could exist. Stay inside it, and you are, at minimum, in the right neighborhood. What the name does not tell you, what the press releases rarely linger on, is that the habitable zone is measuring exactly one thing: temperature. That is it. Everything else, every other condition that makes Earth the kind of place where something can be alive, is left completely off the table. Consider what Earth actually has going for it beyond orbital distance. There is a magnetic field generated by the churning of molten iron in the planet's core. That field deflects the solar wind, a constant stream of charged particles pouring off the sun. Without it, the solar wind would gradually strip hydrogen from the upper atmosphere. Over hundreds of millions of years, it would erode the air itself. Mars almost certainly had liquid water once. Mars lost its magnetic field early in its history, and its atmosphere thinned to almost nothing. Today, the surface of Mars receives radiation levels that would be lethal to most life on Earth. Mars sat at the outer edge of the habitable zone when it had water. Being in the zone was not enough. Then there is plate tectonics. Earth's crust is broken into enormous moving plates that slide, collide, and dive beneath one another on timescales of millions of years. This process does something critical. It cycles carbon. Carbon dioxide gets pulled out of the atmosphere through weathering of rocks, gets carried into the ocean, gets deposited as carbonate minerals, and eventually gets dragged down into the mantle, where subducting plates descend. Volcanic activity then releases it back into the atmosphere. This cycle acts as a thermostat. When the planet warms, weathering accelerates, more carbon gets pulled from the air, and the greenhouse effect weakens. When the planet cools, weathering slows, carbon accumulates, and temperatures recover. Without that feedback, Earth's temperature would drift. It would not stay stable for billions of years. Whether Kepler-452b has plate tectonics is completely unknown. Whether it has an active core generating a magnetic field is completely unknown. These are not minor details. The Moon deserves its own mention here. Earth's axial tilt, the angle at which the planet leans relative to its orbit, determines the severity of seasons. That tilt is currently about 23.5 degrees. It wobbles slightly over long periods, but it stays within a relatively narrow range. The reason it stays stable is the Moon. The gravitational influence of a large nearby moon acts as a stabilizer. Without it, Earth's axial tilt could wander dramatically over millions of years, swinging between near zero and angles above 80 degrees. At extreme tilts, polar regions would bake in continuous summer sunlight for half the year and plunge into months of total darkness. Climate zones would shift violently. Whether Kepler-452b has a large moon is not something anyone has been able to determine. It is too far away and too small for that level of detection. Jupiter is the last piece of this picture, and it is a strange one. Jupiter's gravitational influence sweeps through the outer solar system and deflects a large fraction of the comets and asteroids that would otherwise be on trajectories toward the inner planets. Earth still gets hit. The history of mass extinctions proves that. But the rate of bombardment is lower than it would be in a solar system without a massive outer planet acting as a gravitational buffer. A world in the habitable zone, around the right kind of star, with the right temperature, could still be sterilized repeatedly by asteroid impacts. If no such buffer exists in its system, whether Kepler-452b's solar system contains anything comparable to Jupiter is something current instruments cannot answer. The TRAPPIST1 system makes all of this painfully concrete. TRAPPIST1e sits in the habitable zone of its star. By some physical measurements, it resembles Earth more closely than Kepler-452b does. Its mass, radius, density, and surface gravity all fall close to Earth's values. It checks the orbital distance box. Then James Webb looked at it. What came back were tentative hints of methane in the spectrum, but hints so ambiguous that scientists cannot confirm whether they represent an atmosphere at all, or whether the signal is coming from the star itself. A world in the habitable zone, matching Earth's physical dimensions, and nobody knows if it has any air. The habitable zone told researchers where to look. It did not tell them what they would find. This is the thing about the phrase Earth's twin that was always doing too much work. A twin implies resemblance across every dimension that matters. Same face, same height, same voice, same history. What a habitable zone confirms is that a planet has one address in common with Earth. It orbits its star from a distance that permits liquid water in principle. That is a single coordinate in a space defined by dozens of coordinates. Biochemistry requires more than the right temperature. It requires the right chemistry cycling through rock and ocean and atmosphere over geological time. It requires stability across billions of years, not just in temperature, but in radiation environment, in impact rate, in atmospheric composition. Earth delivers all of this, and the reasons it delivers all of this reach deep into the planet's internal structure, its orbital history, its neighbors, its moon. None of those things appear on the habitable zone chart. Kepler-452b occupies the right address. What happens inside that address, what the planet is actually made of at depth, what its core is doing, what its surface looks like, what gases fill its sky, if any do, remains beyond the reach of anything humans have yet built. Orbital distance is one variable in a system with dozens of variables, and ticking that box while leaving the others blank tells you very little about whether a world is actually alive. The most important unknown about Kepler-452b, the one that would settle most of the other questions, is what its atmosphere looks like. Everything else, the orbital distance, the star type, the surface gravity, feeds into a single central question. Does this planet hold onto enough gas to keep liquid water stable? Does that gas trap enough heat to stay warm, or too much heat to stay livable? The atmosphere is where habitability either survives or collapses, and right now, we have no idea what it looks like. Here is what we can reason through from the numbers we do have. Kepler-452b is roughly 5 times more massive than Earth. That matters enormously for atmospheric retention. Gravity is what holds an atmosphere against a planet's surface, pulling gas molecules back down before they can escape into space. A heavier planet pulls harder. Mars, which has only about 1/10 of Earth's mass, lost most of its atmosphere billions of years ago because its gravity simply wasn't strong enough to hold on. Kepler-452b has the opposite problem. Its gravity is so strong that almost anything it ever collected, it kept. Whatever gases were present when this planet formed have almost certainly stayed. The atmosphere, if one exists, has had 6 billion years to accumulate and thicken. That sounds reassuring until you think about what a thick atmosphere actually does. Venus is the lesson here. Venus has a thick atmosphere, thick enough to crush a poorly designed spacecraft on descent. The pressure at the Venusian surface is about 90 times what you feel standing at sea level on Earth. The atmosphere is almost entirely carbon dioxide, and the greenhouse effect it creates has pushed surface temperatures to around 465 degrees Celsius. Hot enough to melt lead. Hot enough that the surface glows a dull red in the dark. Venus sits only slightly closer to the Sun than Earth does. The difference in solar energy it receives is not dramatic. What is dramatic is what happened to its atmosphere. And on Kepler-452b, with its stronger gravity holding gases in place over 6 billion years of a slowly brightening star, a Venus-style outcome is not a remote possibility. It is one of the most plausible scenarios on the table. The range of outcomes is genuinely wide. On one end, you have a world with a dense carbon dioxide blanket, crushing pressure, and temperatures that would destroy any chemistry we associate with life. On the other end, you have a world that somehow maintained a nitrogen-oxygen balance similar to Earth's, with liquid oceans and breathable air. In between sits everything else: a sulfur-rich reducing atmosphere, a thin remnant layer of nitrogen, a hydrogen envelope, something with no analogue in our own solar system. We cannot rule any of these out. We cannot confirm any of them. The planet is 1,400 light-years away, and the tools required to answer the question simply do not reach that far. To understand why, it helps to look at what the James Webb Space Telescope has actually been able to do, because Webb is the most powerful atmospheric analysis tool humanity has ever built. The way telescopes probe exoplanet atmospheres is through a technique called transmission spectroscopy. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths of light. By measuring which wavelengths get blocked during that transit, astronomers can identify specific gases: carbon dioxide, methane, water vapor, oxygen. It is an extraordinary method. It works. And it has hard limits built directly into the physics. The signal you are trying to detect is tiny. Even for a large planet with a thick atmosphere, the dip in starlight caused by atmospheric absorption is a fraction of a percent of the total brightness. To pull that signal out of the noise, you need many transit observations stacked together. You need the star to be close enough that its light arrives with sufficient intensity to work with. Webb has been pointed at the TRAPPIST system, which sits roughly 39 light-years away. At that distance, with a small red dwarf star, the observations are difficult. Researchers have used dozens of transit measurements to look for atmospheric signatures around TRA-PPIST-1e. The results are tentative at best. As of the most recent published data, it remains genuinely uncertain whether TRA-PPIST-1e even has an atmosphere. 39 light-years with our best telescope, and we cannot yet confirm something as basic as whether the atmosphere exists. Kepler-452b is 1,400 light-years from Earth. That is 36 times further than TRA-PPIST-1e. The signal from Kepler-452's atmosphere would arrive at our instruments 36 times fainter, buried in 36 times more noise, requiring observation time that scales in ways that make the exercise essentially impossible with current technology. Webb was not designed to study systems at this distance, and the engineering challenges of building a telescope powerful enough to pull atmospheric chemistry from a planet at 1,400 light-years are not minor refinements to existing designs. They represent a completely different class of instrument, orders of magnitude beyond what Webb can do. There is something almost mocking about this situation. We have enough information about Kepler-452b to have serious scientific arguments about whether it might be habitable. We can calculate its orbital period to within a day. We can estimate its diameter, its mass, its surface gravity. We can describe the spectrum of its host star with precision. And the one piece of information that would actually answer the question, the chemical composition of whatever surrounds its surface, sits completely out of reach. The planet offers just enough data to be tantalizing and not nearly enough to be conclusive. Some researchers have proposed next-generation telescope concepts that could eventually extend transmission spectroscopy to more distant systems. The proposals involve space-based observatories, with mirror diameters measured in the tens of meters, vastly more collecting area than Webb's 6.5-meter primary. These are concepts. Some have preliminary funding discussions attached to them. None are scheduled for launch. The timelines being discussed are measured in decades, not years, and even the most optimistic designs would struggle with a target at 1,400 light-years. At 1,400 light-years, that answer is not coming anytime soon, with any instrument humanity is currently planning to build. Within days of NASA's announcement, the SETI Institute pointed radio antennas at the location of Kepler-452b and started listening. This was not an impulsive decision. The SETI Institute had been waiting for exactly this kind of target. A rocky world, orbiting a sun-like star sitting inside the habitable zone, with an age suggesting it had been there long enough for something to happen. The Allen Telescope Array in Northern California, a collection of 42 radio dishes working in concert, swung toward the constellation Cygnus and began scanning the frequencies. The logic was straightforward. If Kepler-452b had harbored intelligent life for even a fraction of its 6 billion-year history, and if that life had developed radio technology, some of those transmissions might have been leaking out into space for millions of years. At 1,400 light-years, signals sent 1,000 years ago would already be passing through our borehood. The math was not unreasonable. The hope was not irrational. What they heard was nothing. To be precise, they heard what the universe always sounds like at those frequencies. Background hiss, pulsars, distant galactic noise. Nothing that looked like a structured signal. Nothing that repeated with the kind of regularity that suggests intention. The Allen Array listened, and the direction of Kepler-452b gave back silence. The same silence it had always given back. The same silence that greets every targeted search astronomers have ever run at every promising candidate. Here is the first thing to understand about that silence. It is not nothing. Silence is data, the absence of a detectable signal from a given direction, after a careful search at specific frequencies, actually tells you something. It tells you that if there is a civilization at Kepler-452b transmitting radio waves, it is either not transmitting in the directions and frequency ranges we searched, or it is transmitting at power levels too faint for us to detect from this distance, or it is not transmitting at all. Those are meaningfully different scenarios, and none of them rule out life. Seth Shostak, a senior astronomer at the SETI Institute, put the result in context in a way that stuck. Bacteria, trilobites, dinosaurs, he noted, all spent time on Earth without building radio transmitters. This sounds obvious when you say it out loud. It implies something important. Radio technology represents an extraordinarily narrow slice of the timeline of any biosphere. Life on Earth existed for roughly 4 billion years before anything on this planet generated a detectable electromagnetic signal. 4 billion years of bacteria, algae, fish, reptiles, and mammals, none of it producing anything a distant telescope could identify as evidence of intelligence. A civilization capable of broadcasting radio waves has existed on Earth for less than 2 centuries. If some alien observatory had been scanning our solar system for the previous 4 billion years, they would have found exactly the same thing. SETI found pointed at Kepler-452b. Quiet. This reframes the silence immediately. Kepler-452b could be covered in microbial life. It could host complex ecosystems. It could have animals, forests, oceans teeming with creatures, and still return nothing to our antennas. Radio technology is not a natural development. It requires a specific chain of discoveries, materials, industrial infrastructure, and historical accident that may or may not occur on any given world, regardless of how long life has been running there. But the age of the system still nags. 1.5 billion extra years is not trivial. On Earth, the difference between 500 million years ago and today is the difference between simple marine invertebrates and a species capable of launching telescopes into orbit. Another 1.5 billion years layered onto Earth's timeline is almost unimaginable in its implications. If intelligence emerged on Kepler-452b, even roughly on the same schedule it emerged here, the civilization there could be 1.5 billion years more advanced than we are. A civilization that old, if it still exists, if it ever developed radio, would have had time to evolve past radio in ways we cannot conceive, the way a species that used smoke signals 10,000 years ago has since developed fiber optic cables and microwave towers. They might have abandoned electromagnetic communication entirely. They might communicate in ways that pass through our detectors without triggering any recognition, or they never existed at all. This is the uncomfortable branch of the logic tree that the silence keeps pointing toward. Maybe the chain of events that produced intelligent, technology-using life on Earth is so improbable that 6 billion years and a hospitable environment are not enough to make it likely anywhere else. Maybe Kepler-452b ran through its entire geological history, produced microbial life and nothing more, and has been sitting quietly ever since. Maybe it produced complex life that never reached intelligence. Maybe intelligence emerged and something ended it, long before any of its transmissions could travel 1,400 light years to reach us. Each of these possibilities is consistent with the silence. There is one more scenario worth holding in mind. A civilization sufficiently advanced might have reasons to stay quiet, not because it is incapable of broadcasting, but because broadcasting into an unknown universe is not obviously a safe choice. Some researchers have argued that detectable civilizations may be rare, not because civilizations themselves are rare, but because they learn relatively quickly to minimize their electromagnetic footprint. This would mean the galaxy could be full of intelligent life that has simply decided, or evolved, to be invisible. That possibility is not comforting. It carries its own weight. None of this resolves anything. The silence from one targeted search using one telescope array over a limited frequency range tells us only what it tells us. It rules out a narrow class of strong, directed, detectable broadcasts from that region of the sky. The broader question of what is happening on Kepler-452b, whether it hosts life, whether it ever did, whether anything there is aware that something 1,400 light-years away named it and pointed instruments in its direction, remains completely open. And on top of everything else already established about this world, the unanswered radio silence stacks as one more layer of unresolved strangeness. The silence from Kepler-452b's direction is not a surprise, and it is not a comfort, and it does not tell us anything definitive about what is happening there. The light arriving at Earth from the Kepler-452 system tonight left that star around the year 625 CE. That is not a metaphor or an approximation. It is simply what the speed of light means at this distance. Every photon hitting a telescope mirror right now, every data point used to describe the planet's size and orbit and host star's temperature, every detail in every paper ever published about Kepler-452b, all of it is a portrait of a system as it existed during the early medieval period on Earth. Muhammad had not yet been born. The Byzantine Empire still controlled large portions of the Mediterranean. The city of Rome had been sacked twice in living memory and was a fraction of its former population. That is the world that existed when the light you are currently receiving from Kepler-452b. All of it is a portrait of a system as it existed during the early medieval period on Earth. 52 began its journey. This is the part of the distance problem that does not show up in press releases. The 1,400 light-year figure gets reported as a travel problem, a question of how long it would take to get there. But the light delay is something different. It means we are not observing this system. We are observing a record of this system. There is a distinction there that matters enormously. A photograph of a building tells you what the building looked like when the shutter clicked. It tells you nothing about whether the building is still standing. When Hubble detected a ripple moving through Betelgeuse's atmosphere after years of watching, astronomers understood clearly that they were not seeing the star's present behavior. They were seeing behavior from centuries ago, arriving now. The light leaving Betelgeuse tonight left around the year 1376. For Kepler-452, the lag is more than twice as long. Anything happening on that planet or around that star right now will not reach us until the year 3400. The people alive then, if there are people alive then, will be the first humans with any information about what that system looks like today. We are permanently, structurally locked out of the present tense when it comes to Kepler-452b. Think about what 1,400 years of change actually looks like from Earth's side. In 625 CE, there was no English language. There were no nation-states as we understand them. Agricultural techniques used by the majority of the world's population had not changed substantially in centuries. The distance between that world and this one is not just historical trivia. It represents the kind of transformation that 1,400 years of change can produce on a planet with active geology, active biology, and changing atmospheric chemistry. Whatever Kepler-452b was doing when that light left its star, the planet has had 14 centuries more time since then to do something else entirely. The star itself is the more unsettling consideration. Kepler-452 is a G-type star, slightly older than our Sun, and stars this age are still evolving. Slowly, but measurably. The Sun we see from Earth is not the Sun that existed 1,400 years ago. It is fractionally brighter. The same is true of Kepler-452. the star's luminosity in the images and spectra we have analyzed, belongs to a star that no longer exists in exactly that form. The habitable zone shifted slightly while that light was traveling. The amount of energy hitting Kepler-452b changed. By how much and in which direction are things we can calculate based on stellar models, but we cannot confirm them observationally, because the observations we have are old. Here is what this does to any claim about Kepler-452b's habitability. Every statement about this planet, that it orbits in the habitable zone, that it likely has a rocky surface, that it receives roughly the right amount of stellar energy for liquid water, every single one of those statements carries a hidden qualifier. It did those things 1,400 years ago. Whether it still does them is a question the laws of physics prevent us from answering with any telescope currently in existence or currently planned. We are doing something strange when we discuss this planet in the present tense. We are describing the past and calling it now, because that is all the information we have, and all we will ever have at this distance. The strangeness gets stranger when you push on it. Suppose something dramatic happened on Kepler-452b 500 years ago. A significant shift in atmospheric composition. A massive volcanic event large enough to alter surface conditions. A change in the planet's reflectivity visible from light years away. None of that information has reached us yet. It is still traveling. It left the system in the 1500s and will not arrive here until the 2900s. We would be looking directly at this planet, pointing the most sensitive telescopes ever built at it, and seeing a version of it that predates the event entirely. The signal of whatever happened next is somewhere in the gap between that star and our detectors, closing the distance at the speed of light, with no way to accelerate. Astronomers who study Betelgeuse wrestle with this same problem at shorter range. For Betelgeuse, the delay is around 650 years. The dimming event that captivated the world in 2019 and 2020 was not a 2019 event on the star. It was a centuries-old event, arriving on a particular schedule. There is a real possibility, not a dramatic flourish, but an actual astronomical possibility, that Betelgeuse has already gone supernova, and the light from that explosion is traveling toward us right now. The same logic applies to Kepler-452. Whatever that system looks like at this moment in cosmic time, we have no access to it. We have a 1,400-year-old image, detailed and precise, and permanently out of date. The telescopes are pointed. The data is real. The numbers are accurate. And what they describe is a ghost, a detailed, scientifically rigorous ghost of a world that existed when plague was still reshaping the populations of continents, and the largest structures most humans would ever see in their lifetimes were made of stone and timber. Whatever Kepler-452b looks like right now, whether it is alive or dead, or something in between, we will not have any idea until sometime around the year 3400. 26 million years sounds like a number someone made up to sound dramatic, so it is worth spending a moment on what it actually represents in terms of things that happened on Earth. New Horizons launched in 2006. It crossed the distance to Pluto in 9 years, moving at roughly 59,000 kilometers per hour. That felt fast. It was the fastest spacecraft humanity had ever sent anywhere. Scientists celebrated. Then someone did the arithmetic for Kepler-452b. At that same speed, the journey would take approximately 26 million years. Not 26,000, not 260,000, 26 million. The number sits there, and it requires context before it means anything at all. 26 million years ago, the Alps were still being pushed upward by colliding tectonic plates. The mountain range that today draws tourists and climbers and painters was an unfinished construction site, rising slowly out of what had been a shallow sea. Hominids did not exist. The entire genus that would eventually produce human beings had not yet appeared on the planet. The common ancestor shared by humans and chimpanzees was still alive and would not split into separate lineages for another 10 million years. Everything that you would recognize as human history, every civilization, every war, every invention, every recorded word, fits inside the last fraction of a percent of that travel time. If New Horizons had launched 26 million years ago, it would be arriving at Kepler-452b right now. The crew, had there been one, would have been something other than human when they left. This is what 1,400 light years actually means when you translate it into travel. Not an inconvenience, not a long voyage, a barrier of a different kind entirely, something that operates on geological time rather than human time, something that swallows civilizations whole and asks for more. Now, someone will point out that New Horizons was not designed for interstellar travel. Fair, so push the number. Imagine a spacecraft moving at 1% of the speed of light. No such spacecraft exists. We have no engineering blueprint for building one. The energy requirements alone sit somewhere beyond anything our current civilization can produce, or even clearly imagine producing. But set that aside. Assume it exists. At 1% of the speed of light, the journey to Kepler-452b takes 140,000 years. Modern humans have existed for roughly 300,000 years. So a one-way trip at a speed we cannot currently approach would consume nearly half of the entire lifespan of our species on Earth. Every language spoken today would be dead long before arrival. Every government, every religion, every cultural institution that exists would be unrecognizable or gone. Push harder, 10% of the speed of light, the kind of velocity that would require propulsion technology that currently belongs to science fiction. That journey takes 14,000 years. 14,000 years ago, agriculture did not yet exist. Writing had not been invented. The first cities were still thousands of years away. The gap between then and now, every dynasty and empire and discovery that fills the history books, equals less than the travel time at 10% of light speed. The people who launched would have no relationship whatsoever to the people who arrived. Not culturally, not linguistically, possibly not biologically. This is where the generation ship enters the picture. The concept has been written about and debated for decades. A vessel large enough to sustain a self-contained human population across thousands of years of travel. People born in transit. People dying in transit. Children raised knowing nothing of Earth except what records and stories survived the journey. Hundreds of generations cycling through before the destination appears in the forward cameras. Think about what that means for continuity. A civilization launched from 21st century Earth would need to preserve its purpose, its knowledge, its social cohesion across a time span longer than all of recorded human history. Every generation would need to choose to continue the mission that none of them chose to begin. Every child born on that ship would be there without consent, raised inside a metal container drifting through interstellar space, tasked with completing a journey started by people they cannot meaningfully imagine. And at the end of it, the crew that arrived would share almost nothing with the crew that departed. Different language, different values, different understanding of what Earth was or why they were sent. Whatever connection existed between the origin and the destination would be a thread stretched across geological time until it held almost no tension at all. And that scenario still requires technology we cannot build. The propulsion, the closed-loop life support running without failure for thousands of years, the shielding against interstellar radiation across a journey that long. Every one of those problems is unsolved. Some of them may be fundamentally unsolvable with any near-future engineering. The generation ship is not a plan. It is a thought experiment that reveals the scale of the problem more clearly than any number alone can. What makes this genuinely strange is the asymmetry of it. We know the planet is there. We have measured its orbital period to within days. We have estimated its diameter, its likely mass, its distance from its star, the age of that star, the temperature of its habitable zone. We can point a telescope at the exact position in Cygnus where it sits and describe it in meaningful detail. The knowledge is not the barrier. The knowledge came easily, relatively speaking. A space telescope, a transit detection, a press conference. The knowing took a decade. The going would take civilizational timescales that no political system, no funding structure, no cultural institution that has ever existed on Earth could sustain. There is something almost mocking about it. The universe arranged things so that finding another Earth is possible, in the sense that a sufficiently sensitive telescope can detect one from here. But reaching it is so far beyond possible that the word impossible barely covers it. Not impossible in the way that breaking the sound barrier was once impossible, a thing that required clever engineering and eventually fell. Impossible in the way that stands behind physics itself, behind the hard limits of how fast mass can move through space and how long biological creatures can maintain a purpose across millennia. The distance to Kepler-452b does not get easier the more carefully you look at it. Every attempt to make it concrete, to translate light years into years of travel, produces numbers that collapse the imagination rather than expand it. There is no trajectory from here to there that does not require either physics we have not discovered or a commitment of time that dwarfs the entire history of human civilization. Kepler-452b is not the only candidate for Earth's twin, and the others do not make the picture any more comfortable. While astronomers were wrestling with the implications of Kepler-452b, another system was pulling attention in a different direction entirely. The TRAPPIST-1 system sits roughly 39 light-years from Earth. That sounds like a trivial distinction until you set the two numbers side by side. 39 light-years versus 1,400 light-years. At New Horizons speed, TRAPPIST-1e would take something closer to 700,000 years to reach rather than 26 million. Still an incomprehensible span of time by any human measure, but it is a fundamentally different category of distance. Telescopes can study it with more resolution, more detail, more patience. What they found when they looked carefully was a world that on paper matches Earth more precisely than Kepler-452b ever did. TRAPPIST-1e is close to Earth in mass, close in radius, close in density, close in surface gravity. The numbers line up in a way that made some researchers call it the most Earth-like planet yet found, in terms of raw physical similarity. Kepler-452b is bigger, heavier, pulled harder by its own gravity. TRAPPIST-1e feels, by comparison, almost familiar. If you could somehow stand on its surface, you would weigh roughly what you weigh here. Your bones would not strain. Your heart would not labor under doubled gravity. On that single axis, TRAPPIST-1e wins the comparison easily. The problem is that mass and radius are not the whole story, and the star TRAPPIST-1e orbits changes everything about it. TRAPPIST-1 is not a star like our Sun. It is a red dwarf, a dim, cool, ancient ember compared to the bright yellow star Kepler-452b circles. Red dwarfs make up the vast majority of stars in the galaxy. They live for an extraordinary length of time, far longer than Sun-like stars. They are small enough that their habitable zones sit much closer to the star's surface than ours does. To receive enough warmth to sustain liquid water, a planet around a red dwarf has to huddle in tight. TRAPPIST-1e does exactly that. Its year lasts only about 6 Earth days. It completes an entire orbit in the time it takes Earth to move through roughly 1 week of its own calendar. That proximity carries a consequence nobody can engineer around. Red dwarfs are not gentle. They produce stellar flares, sudden violent eruptions of radiation that can be far more intense relative to the star's baseline output than anything our sun regularly produces. A planet sitting close enough to a red dwarf to be warm is also close enough to be periodically blasted with bursts of ultraviolet and X-ray radiation. Over billions of years, those flares can strip away a planet's atmosphere the way wind strips paint off an old building. Slowly, relentlessly, without stopping. Whether TRAPPIST1e has held onto an atmosphere through this process is one of the central questions in exoplanet science right now. The James Webb Space Telescope has turned toward this system with precisely this question in mind. Early observations picked up what looked like tentative hints of methane, intriguing data. Not confirmation. Scientists are careful about the distinction, and they should be, because the source of those hints could be the planet's atmosphere, or it could be the star itself producing a false signal. That question has not been resolved. Then there is the tidal locking problem, which is worth sitting with for a moment because it is strange in a way that does not have a clean Earth-based analogy. When a planet orbits close enough to its star, gravity eventually synchronizes the planet's rotation with its orbit. The same face always points toward the star. The opposite face always faces away. Permanent noon on one hemisphere, permanent midnight on the other. Our moon does this with Earth, which is why we only ever see one side of it from the surface. TRAPPIST1e is almost certainly tidally locked to its star. That means one half of the planet bakes under continuous starlight, day after day, year after year, for billions of years. The other half sits in permanent darkness, frozen, cold in a way that has no daily relief. What would the boundary between those two hemispheres look like? Potentially a narrow ring around the planet where temperatures fall somewhere between the extremes. A twilight band where the conditions might theoretically be tolerable. Some researchers have suggested this terminator zone could sustain liquid water if the atmosphere was thick enough to redistribute heat from the day side to the night side. It is a compelling idea. It is also entirely hypothetical, dependent on an atmosphere whose existence has not been confirmed. Strip away the atmosphere, and the terminator zone offers no shelter. The day side roasts, and the night side freezes, and nothing circulates between them. So here is where the comparison lands. Kepler-452b orbits a star almost identical to our Sun. It has stable, predictable light output. No evidence of extreme flaring. A G-type star running through a long, quiet, yellow dwarf life. The planet itself is in a reasonable orbital position, taking 385 days to complete one lap. It receives sunlight in a rhythm that resembles Earth's in the ways that matter most for long-term stability. But it is 1,400 light-years away, which is effectively forever by any travel standard humans have ever achieved, and its surface conditions might have been transformed by billions of years of stellar brightening into something resembling Venus more than Earth. TRAPPIST1e is 39 light-years away. It matches Earth in gravity and density in a way Kepler-452b simply does not. But it orbits a flaring red dwarf, so closely that its year runs in days rather than months. Its atmosphere may have been eroded over geological time, and it is almost certainly locked in place with one face burning and one face frozen. The James Webb Space Telescope can actually point at it with meaningful results, which is something it cannot do for Kepler-452b with any practical hope of atmospheric characterization. And what Webb has found so far has raised more questions than it has answered. Neither candidate offers comfort. Neither one is a clean discovery of another Earth. They are both, in their own distinct ways, warnings about how much harder the real picture is than the headlines made it sound. The closer the candidate, the more easily we can study it, and the more we study it, the more problems we find. Researchers developed the Earth Similarity Index as a way to move beyond pure press release language and put a number on how Earth-like a planet actually is. The idea was straightforward. Instead of describing a planet as Earth-like in a paragraph of qualifications, you run its physical measurements through a formula and get a single score between 0 and 1. Earth scores exactly 1.0. Mars scores around 0.64. Venus comes in at roughly 0.44. A barren rock with no atmosphere and the wrong temperature drifts towards 0. The closer a planet's score is to 1.0, the more it resembles home. At least on paper, the index pulls from 4 measurements: radius, bulk density, escape velocity, and surface temperature. These are not arbitrary choices. They are the properties most directly tied to whether a planet is rocky, whether it is the right size to hold an atmosphere, and whether its surface sits in a temperature range where liquid water is theoretically possible. For each property, the planet's value gets compared to Earth's value, weighted and folded into the final number. The math is clean. The variables are measurable. The result feels authoritative. Kepler-452b scores somewhere around 0.83 on this index. That sounds impressive. For context, it is one of the highest scores ever recorded for a confirmed exoplanet. When the number circulated after the 2015 announcement, it seemed to validate everything the headlines were already claiming. Here was a quantitative tool, something rigorous and scientific, and it was saying that Kepler-452b was 83% similar to Earth. That framing traveled fast. What got left behind was the question of what that 83% was actually measuring. Here is the problem. The ESI scores 4 variables. Earth's habitability depends on dozens. The index does not measure magnetic field strength. A planet without a strong magnetic field has no reliable shield against stellar wind, and stellar wind strips atmospheres over billions of years. Mars almost certainly lost most of its atmosphere this way. The ESI cannot tell you whether Kepler-452b has retained a protective magnetic field for 6 billion years, or whether that field has weakened, or whether it ever existed at the right strength in the first place. It does not measure plate tectonics. On Earth, plate movement cycles carbon through the crust and atmosphere, acting as a long-term thermostat that keeps surface temperatures from drifting too far in either direction. Without that cycling, a planet can accumulate too much carbon dioxide and cook, or lose too much and freeze. Plate tectonics is one reason Earth stayed habitable long enough for complex life to emerge. Whether Kepler-452b has active tectonics is completely unknown, and the ESI does not ask. It does not measure axial tilt stability. Earth's axial tilt stays relatively consistent over long periods, partly because of the Moon's gravitational influence. That stability keeps seasons from becoming extreme. A planet with a wildly varying tilt could swing between ice ages and furnace periods on timescales too short for life to adapt. The ESI score for Kepler-452b says nothing about this. The planet's tilt could be stable, or it could wander. Atmospheric composition does not appear in the index at all. Whether a planet breathes nitrogen and oxygen, or carbon dioxide and sulfur dioxide is irrelevant to the ESI calculation. 2 planets could share identical scores while one has an atmosphere that would support complex life, and the other has an atmosphere that would crush and poison anything that tried to exist there. The score treats them the same. Stellar activity is absent as well. Red dwarf systems get penalized by other assessments. But the ESI in its basic form is a planetary index, not a stellar one. A planet orbiting a star that regularly blasts its surface with intense radiation could score well on the ESI, while being scoured clean by flares every few years. The number does not know and does not care. What you are left with is an index that measures physical resemblance at a very specific level. It is asking whether the planet is roughly the right size, roughly the right density, and roughly the right temperature. Those are necessary conditions. They are nowhere close to sufficient ones. A planet that fails those checks is almost certainly not habitable. A planet that passes them has cleared only the first gate in a very long sequence. Scientists who developed the ESI understood this. The index was designed as a sorting tool, a way to triage the thousands of exoplanet candidates and identify which ones were worth studying more closely. It was never meant to be the last word. The problem is that once a number exists, it gets used. It shows up in articles without its caveats. It becomes the headline. Kepler-452b scores 0.83 on the Earth Similarity Index. Becomes Kepler-452b is 83% Earth-like, and that phrase does a kind of damage to public understanding that is difficult to undo. This is not a story about scientists misleading anyone. The researchers who study these worlds are careful with their language. The problem is the distance between a careful scientific assessment and what survives the journey into a headline. Complex probability distributions, full of uncertainty and conditionality, get compressed into single confident claims. A planet that might be rocky, and might have the right temperature, and might have retained an atmosphere, and might have liquid water, becomes Earth's twin. The might drops out at every step. The ESI is a useful instrument. It identified Kepler-452b as worth studying. It helped focus attention on a genuinely interesting system. But the number it produces is a starting point dressed up in the grammar of a conclusion. A high ESI score means a planet resembles Earth in a handful of measurable physical properties, which is a long way from meaning it is a place where anything could live. If Kepler-452b is not alone as a potentially habitable world, and the evidence strongly suggests it is not, then the galaxy contains an enormous number of places where life could theoretically have emerged. The Kepler mission alone, surveying a small patch of sky, found thousands of exoplanets. Extrapolate that across the full Milky Way, with its estimated 400 billion stars, and the number of rocky planets sitting in habitable zones runs into the hundreds of millions, possibly more. The math is almost impossible to absorb. If even a tiny fraction of those worlds developed life, the galaxy should be crowded with it. And yet, nothing. No signal, no artifact, no transmission cutting through the background noise of space. Decades of listening, and the universe has returned only silence. This is not a small observation. It is one of the strangest facts in all of science. The equipment exists. The methodology is sound. SETI researchers have swept enormous volumes of sky across enormous ranges of frequency. The Allen Telescope Array has logged millions of hours of listening. The result is the same every time. Whatever is out there, it is not announcing itself. This is what makes Kepler-452b more than just a distant curiosity. It sits at the center of a question that has no comfortable answer. If the galaxy holds hundreds of millions of potentially habitable worlds, and if life tends to emerge when conditions allow, then civilizations should exist, many of them, some of them far older than ours, some of them with billions of years of head start. The silence should be impossible, and yet the silence is what we have. The concept astronomers and philosophers use to frame this problem is called the Great Filter. The idea is straightforward in outline and terrifying in implication. Something is preventing the galaxy from filling up with detectable civilizations. Either the filter sits behind us, meaning that the emergence of life, or complex life or intelligent life is so improbable that it almost never happens, making us extraordinarily rare. Or the filter sits ahead of us, meaning that civilizations tend to reach a certain level of development and then stop, collapse, or go quiet. Neither option is reassuring. The first says we are essentially alone. The second says that civilizations like ours tend not to survive. Apply this to Kepler-452b directly. The planet has been orbiting in what was once a temperate zone for roughly 6 billion years. If life emerged there early, it had 1.5 billion more years than Earth to develop complexity, intelligence, technology. By any reasonable timeline extrapolated from our own history, a civilization that started where Earth started but had 1.5 billion extra years should be incomprehensibly advanced. It should have spread. It should have built things detectable across interstellar distances. It should, at minimum, have produced radio transmissions that would have been washing over Earth for hundreds of millions of years before our planet even had multicellular life. We have heard none of it. The silence from that direction is total. What does that silence mean? Here is where it gets genuinely uncomfortable. The absence of a signal is consistent with every possible scenario. It is consistent with no life ever having emerged on Kepler-452b. It is consistent with life emerging and never developing intelligence. It is consistent with intelligence developing and never producing detectable technology. It is consistent with a civilization rising, lasting for a while, and then destroying itself before it could reach far enough. It is consistent with a civilization so advanced it no longer uses radio or any technology we would recognize as technology. The silence does not discriminate between these possibilities. It fits all of them equally. And this is the part that should sit uncomfortably in the back of the mind. We cannot tell the difference between a dead planet and a dead civilization from here. Seth Shostak, a senior astronomer at the SETI Institute, has pointed out that bacteria, trilobites and dinosaurs were all alive on Earth at various points without building anything detectable across space. Life does not automatically produce signals. Intelligence does not automatically produce radio. The chain from simple chemistry to detectable civilization is long and requires every link to hold. Maybe it almost never does. Maybe Kepler-452b got through the first few links and stopped. Maybe it never got past the first one. Or maybe something broke the chain after it had already run most of its length. There is a version of the great filter that is particularly hard to sit with. Suppose life is common. Suppose intelligence is not especially rare. Suppose civilizations do emerge with some regularity across the galaxy. And suppose that the reason we hear nothing is that technological civilizations carry within them the mechanism of their own destruction, that they reach a point of capability beyond which they cannot reliably govern themselves. The filter, in that case, is not behind us. It is somewhere close ahead. The silence of the galaxy would then be a kind of warning, written in the absence of signals rather than in words. Kepler-452b has had long enough, if any of this is happening there, to have been through the entire arc. Whatever sequence of events was possible on that world, the 6 billion year clock has had time to run it. And still nothing reaches us. Not a whisper, not an anomaly in the data that requires a civilization to explain it. Just the steady, indifferent background hum of a universe going about its own business. The terror of Kepler-452b started as a distance problem. 1400 light years. 26 million years at current spacecraft speeds. A photograph that is already 14 centuries old by the time it arrives. Those are the figures that stop people cold when they first work them out. But distance is at least something the mind can hold. It is a large number attached to a familiar concept. The silence is different. The silence is not a large number. It is an absence that stretches across every direction, at every frequency, across every year of listening. And the most unsettling interpretation of that absence is not that we are alone, it is that we might understand, eventually, exactly why we are. The distance to Kepler-452b is terrifying on its own terms, but the silence coming from that direction might be the more important measurement. The honest reason to keep searching for Earth's twin is not that we expect to go there. Nobody sitting in a serious planning meeting at any space agency on Earth is drawing up a mission profile for Kepler-452b. The distance makes that conversation impossible. 26 million years at our fastest spacecraft speed is not a problem that optimism solves. So why does the search continue? Why did NASA build the Kepler telescope in the first place, point it at a patch of sky in Cygnus, and spend years counting the tiny shadows of distant worlds crossing distant suns? The answer is that finding another Earth is not really about that Earth. It is about this one. When you ask whether a world like Kepler-452b exists, what you are actually asking is something more unsettling. You are asking whether Earth is ordinary, whether the specific combination of conditions that produced us, a rocky world at the right distance, orbiting the right kind of star, with the right chemistry and the right age, is something the universe does routinely, or something the universe managed exactly once. That question does not have a small answer. It touches everything. The history of science has a pattern. Every time humanity has decided it occupies a special place, the data eventually suggested otherwise. Earth was not the center of the solar system. The solar system was not the center of the galaxy. The galaxy was not the center of anything. Kepler-452b is another data point in that same argument. Before the Kepler mission launched in 2009, the honest answer to the question of how common rocky planets in habitable zones were was that nobody actually knew. There were theories, there were models, there were estimates ranging from optimistic to deeply skeptical. What there was not was evidence. Kepler changed that permanently. Over 9 years of operation, it found more than 2,600 confirmed exoplanets and thousands of additional candidates. The pattern that emerged from that catalogue was striking. Rocky planets are not rare accidents, they are common. Habitable zone orbits around sun-like stars are not exotic exceptions. They appear throughout the galaxy in numbers that, when you try to estimate the total, run into the billions. That shift in baseline probability is not a small revision. It rewrote the starting assumption of every conversation about life beyond Earth. Before Kepler, the default skeptical position had a certain reasonable weight to it. Maybe Earth was genuinely unusual. Maybe the conditions required were so specific that the galaxy was effectively empty of anything similar. After Kepler, that position requires much more work to defend. The universe, it turns out, makes planets like Earth with something close to enthusiasm. What it does with them afterward remains the open question. This is where Kepler-452b sits in the larger story. It is not just a planet. It is evidence. It is evidence that the recipe works elsewhere, that a sun-like star can produce a rocky world at 1.05 AU and keep it there for 6 billion years. Whether that world is alive, whether it ever was alive, whether the brightening of its star pushed it past some thermal threshold long ago, none of that changes what the planet's existence implies about the galaxy. Rocky worlds and habitable zones exist in large numbers. We now know this. Kepler-452b is one of the cleaner examples in the catalogue. To understand why astronomers found the discovery so significant, you have to remember what every previous candidate was missing. Most of the potentially habitable exoplanets found before 2015 orbited red dwarf stars. Red dwarfs are common, but they are also violent. They flare, they strip atmospheres, they force any habitable planet to orbit so close that tidal lock-in becomes a serious problem. Kepler-452b orbited a G-type star, a star that behaves almost identically to our Sun. That detail mattered enormously. It meant the environmental context was familiar in a way no previous discovery had been. The light falling on Kepler-452b for 6 billion years has been, in terms of its character and spectrum, essentially the same light that falls on us. There is something worth sitting with in that fact. The same kind of light, the same orbital geometry, a year that runs 385 days instead of 365. Seasons, probably. A surface that is almost certainly rocky. Whatever happened on that world, it happened under conditions that are not alien in the fundamental sense. The physics was the same. The chemistry was available. The time was more than sufficient. Whether any of it added up to something is the question that cannot be answered at 1,400 light years with any instrument currently in existence or currently being planned. What the Kepler mission left behind is a different way of thinking about the night sky. Every point of light above us now comes with a statistical weight attached to it. Most sun-like stars probably have planets. A meaningful fraction of those planets are likely rocky. Some fraction of those occupy habitable zones. The sky did not change when Kepler returned its data. The inference about what the sky contains changed completely. That shift is not trivial. It is the kind of shift that, in a century or two, will probably be described as one of the more significant moments in the history of human understanding. And yet the distance remains. All of that knowledge, all of that confirmed probability, and Kepler-452b is still 1,400 light-years away. We can describe its orbital period to within a fraction of a day. We can estimate its diameter, its likely surface gravity, its approximate age. We can calculate how much stellar energy falls on it every second. We cannot send anything there. We cannot detect its atmosphere with any tool we have. We cannot know its current state, because its current state is information that will not reach us until the year 3400. The knowledge is precise, and the gap is absolute, and both of those things are true at the same time. That combination is what makes Kepler-452b genuinely strange as an object of scientific attention. We keep looking at it, keep refining the measurements, keep including it in catalogues and papers and press conferences. Not because any of that brings us closer to it, but because the alternative is deciding the question does not matter. And the question, it turns out, matters quite a lot. The distance is terrifying, the silence is unsettling, and the planet is still there, 1,400 light-years away, doing whatever it is doing, completely indifferent to whether we ever figure it out.